Okay, so welcome back to video 4, and we're going to talk about, this is class 1, video 4, sorry. And this is the section 1/6, the importance of dimensions and units. Now I have modified this part because I think it's important. I taught this course using a different book previously. And so this table you'll see right here is out of Munson's Fundamentals of Fluid Mechanics. It's a really good book. I think this is an important topic related to dimensions, dimensional homogeneity in units, and it's not covered. So you will need this table to be able to do some problems in homework 1. So let's talk about these, like maybe two systems of dimensions, right? Now, I'm not saying units. Be careful not to say units. I mean dimensions, right? And so we have the force, length, and time. For whatever reason, they use capital T. Don't ask me why. Or we could have mass, length, and time. So you could you could maybe, instead of going specific to a SI units or British units, we just say dimensions, right? Just the dimensionality of a parameter. And we can go back and forth in between either one. So regardless, we could either find what the dimensions are in the FLT system or in the MLT system, where we have force, length, and time, or we have mass, length, and time. And the way to connect them is through F equals ma, right? So just note that if you had a force as and you're thinking about a particular unit, the parameters units that you're looking at, look for the force, and if you want to turn it into the MLT system, just replace F with M, L, and T to the minus 2, right? So that'd be, because you have mass, M, and then you have acceleration with this length per second squared, right? Per time squared. So, but it's on the denominator, so it's minus 2, right? Conversely, if instead you wanted to change from the MLT system to the FLT system, you would take mass, any place you saw there was a mass term, and you replace it with a force times length to the minus 1 times time to the squared, right? Which is really just flipping this guy around, right? So it might seem a little confusing, but as soon as we do some examples, you're gonna be like, that's like easy. I totally get that. So like this is the video that you really need for homework related to this class. The textbook we have doesn't have anything like this, or doesn't exactly have this, so I figured this would be a better substitute to give you something to do so that you could learn something instead of just information, right? So in this table, you could do all of this. You could figure all these out on your own, but these are all done for you, right? So you could pick out a few, and notably, so something like I just one jumps out at me. Angle has all of the zeros in all of them, right? Because the angle doesn't really have a dimension, as it is. It doesn't. It's non-dimensional, even though it is. You could make a convert between the units. You could go from degrees to radians or whatever. It still doesn't matter. It doesn't factor into as a dimension. But if you had the density of something, right? Well, it's hard to think of a mass density, I should say, in terms of the FLT system, but it is pretty easy to go mass divided by volume, and which it's going to be length cubed, right? So because it's divided, it's got a minus right in there. Hopefully you can see that. I'll make that a little bigger. Okay. And so then from that, you would just substitute in this right in here, and you would see that you would end up getting F times L to the minus 4 T squared, right? So sometimes it's easier to use one of the system of units to figure the thing out. But if you're trying to balance out, it's sometimes it's advantageous to do one system over another, right? So mass density, definitely easier to figure out here from MLT, not easy to figure out from the FLT system. Let's take another look at another one. We got pressure, right? Pressure would be a good one. That's force per unit area, so force times length to the -2, right? Area is going to be length squared, but it's on the denominator, so it becomes L minus 2. All right, easy in the FLT system, not so easy in the MLT system, right? But you just go ahead and replace that F with this right here, and you're able to come up with that, right, on your own. But this table is here for help, because some systems you might not quite know, right? So we have two terms right here. We just talked about viscosity before. These aren't intuitive. We will work through them at a later date, where we start to get a better feel for why they have these dimensions. For just now, just kind of accept it out of the table that this is what I will use for this. So here we got example 1 for this. And okay, we want to have the question, is this equation dimensionally homogeneous? Now, the title of this section is Importance of Dimensions in Units. This is an example of something you should kind of try to be doing. You've probably already been doing, but you should really just do this throughout your entire career, is to always look for whether an equation that you see is dimensionally homogeneous, because sometimes some proprietary stuff, not stuff out of like your a good textbook, but like stuff that things come out of like codes and standards, this parameter here, this value that you're given, this might actually have dimensions to it. So a good question is this dimensionally homogeneous? So right here, this is going to be volume flow rate, and I should point out there's too many V's. And they like to use, in fluid mechanics books, they like to use capital V for velocity, right? So we need something for volume. So I always use this for volume. You use a cross out in there. And then volume flow is this with a dot, right? Per unit time. So we have a volume flow. Like you think of gallons per minute, right? Or cubic feet per second. That kind of thing. Those are volumetric flows as opposed to mass flows, right? So volume flows. So that's volume flow rate, area, G is gravity, H is height. So we come up to here and take a look at the volume. I don't think the volume flow rate is actually on here, to tell you the truth, for some reason. You have volume here, but you could always find that out for yourself, right? That's pretty easy. L3 is volume, and it's per time, so it's T minus 1. It's going to be equals, I'm going to carry you through this value right here, 0.61. And I'm going to take that 2 out of that square root, just put it over here to the side. And now I'm going to take that area, and I'm going to look and say that, well, the area is going to be L2, right? And acceleration of gravity is LT minus 2, right? Because that's acceleration, so length per time squared. And then it's multiplied by height. But it's the square root of it right here, right? So one thing we should know is that these two right here, this is squared, right? So we could see, I'll rewrite the thing out, even though it's going to take a little more time in here. Points, I'll just carry this through. Square root 2, L2, noteworthy, this becomes L2T minus 2, but we have the square root of it, right? So this whole thing becomes L and T minus 1, right? Because we took the square root of those. And then, of course, we have L squared. I'll write this one down again, square root of 2. And this is L cubed T minus 1. But if you combine that guy with those, right, we'll see that those cancel out. And then you can see that those cancel out. So, yes, it's dimensionally homogeneous. It balances out. You could do a lot with units. You could, but it's a really good thing. We've made sure that this was not some type of proprietary empirical type of thing that actually had units built in there. And now for the next example, the all-important, we brought his name up before, but here he is, the one, the only, Mr. Osborne Reynolds. The Reynolds number, often written out as RE, and you can see that RE, it's a dimensionless number, but we want to show that it's dimensionless and use both systems. Let's use both the FLT and the MLT, right? So Reynolds number is equal to, and there's a bunch of different equations for Reynolds number, but they're all basically the same thing, but sometimes they'll look a little bit different. We have density, mass density times velocity, not volume, that's velocity, times length, and this could be actually some parameter that has a major dimension to it. So sometimes that could be diameter too, by the way. It doesn't have to be length. And then divided by, and this is dynamic viscosity. As opposed to kinematic viscosity. Kinematic viscosity, as we'll learn later, is actually dynamic viscosity divided by density. Because they get put together so often, and you'll even see them right there. That's really just what the difference is. So let's try with the FLT system first. In the FLT system, we'll go one at a time here. We'll say density in the FLT. So that's a hard one, right? We better look it up. That's force, length minus 4 time, So we got FL minus 4 T2, right? And then times velocity, so that's length time minus 1 times length, which is, of course, length, all divided by dynamic viscosity, which we have to look up right here, and that's FL minus 2 T. Yeah. And I find that to put them on the same line together helps me establish this thing. I'll go FL minus 4 T squared L T minus 1 L, and then I'll go F minus 1 L2, and then T minus 1. And then start going through the parameters. Those balance out. Let me go time first. That's easy enough, right? That time kills those two, right? Because you had 2 and then a -1 and a -1 cancel out. And now we have this L to the minus 4. Here's a +1, +1, +2. So there you go. Those all cancel out. So yes, it's dimensionless. But let's go and try it with the MLT system now. We got the Reynolds number, but let's look up. We're going to go for the mass density. We can actually just do that in our heads. ML minus 3, right? For mass density. And then we have velocity. That too is going to be LT minus 1 and times length, right? And now, though, we need the dynamic viscosity in the denominator. And he's going to be, and we want what the MLT system, so he's M, L minus 1, T minus 1. And I'll put them all on the same line. And now he gets a -1 because he was on the denominator. We're moving him up. He's a regular L, no longer a -1, and this no longer a -1 here. So we see the masses cancel out. We have length and -1, but here's a length 1, 2, 3. Okay, so they cancel out. And then lastly, you have T cancels out. So yes, it's dimensionless. Now this is going to come up, and we're going to need to be using this later on in the semester in something called Buckingham pi. It's a way in which we can find what dimensionless parameters exist for a particular application, right? And by using these dimensionless parameters, we could do experiments in a lab and gather data and create curves for varying some of those parameters within a dimensionless number, and then reuse that graph in a new situation, or propose that we do. Sometimes just because you create a curve doesn't mean it's repeatable, but we will find in fluid mechanics that we could create these curves, or people have created curves for you already using dimensionless parameters. And they do it by way of this process called Buckingham pi, and Buckingham pi needs this. So that's the reason why we're learning it. And we are done with video 4.